In this video, we are going to talk about Einstein's general theory of relativity. We are also going to learn about Einstein's field equations, what is a Ricci curvature, how to measure space-time curvature, what is metric tensor, what is manifold, what is Riemannian manifold, and many other important aspects, theories, and ideas of Einstein's relativity. I can promise you this much, that if you watch this video till the end, you will get a clear, comprehensive, and a solid understanding of Einstein's general relativity. There won't be too much of difficult mathematics involved in this video. I have avoided derivations of curvature and tensors, and I have kept it simple so that you can understand each and every aspect of this theory in a clear and comprehensive manner. My name is Shaunak and you're watching this video from Physics for Students. I welcome you to my channel. Before we start ahead and go with this, I would like to tell you what are the topics that we are covering. I have avoided the technical names, so I have just laid it down in this way. We are first going to learn what are the different components of Einstein's field equations. Then we learn that what causes space-time curvature, how matter actually moves in space-time, and how do we measure the movement. We also want to learn that how volume changes in space-time, which is an important aspect. We are next going to look into how do we measure curvature through metric tensor, what is the rubber sheet analogy called, and how do we measure movement, what is the manifold, which is an important aspect of general relativity, who discovered manifold, Riemannian manifold, what is a Riemannian metric, and finally all allocated in the big picture. So this would be a fairly detailed video. You can have a pen and a paper, or you can take pause, you can take notes. That would be better because we will be touching with all the aspects of relativity, and this is one complete video which is going to give you a thorough understanding of general relativity. So this is one photograph which I would like to show you, and here is a small quiz. As you can see, there is a train on which the field equations have been written. So what is this about? Please let me know in the comment box what is this about and where this abandoned train cargo is located. First, we would start in understanding what are the components of Einstein's field equations. So first we would understand that we all know that this is basically Einstein's field equations, which we all know is quite famous. So first of all, what we want to know is that what is R mu nu? So R mu nu denotes what is called a Ricci curvature tensor. R denotes what is called a Ricci curvature scalar. G mu nu actually denotes metric tensor. Lambda is the famous cosmological constant. Then we get the capital G, which is the good old Newton's gravitational constant. C, which is the speed of light. And T mu nu, which is known as stressenergymomentumtensor. Well, because this video will be concerned to relativity, so we will be learning about the Ricci curvature tensor, the Ricci curvature scalar, what is the metric tensor, and what is T mu nu, that is a stress energy momentum tensor. The gravitational constant, speed of light, and the cosmological constant I'm avoiding so that it would become too lengthy, and we will deal it in the another part of the video. So these are the components of Einstein's field equations, and the underlined red are the one which we are going to learn in this video. First of all, let us understand that as we have seen that this Greek letter mu and nu, what does it denote? So mu nu actually denotes space-time in 4 dimensions. So the first 0 component denotes time. The first would be x-axis, the y-axis, and the z-axis. Let us see how it can be demonstrated visually. So if I've got an x and y kind of an axis, then this t would be the time, and xyz would be the space. So 3 dimensions of space plus 1 dimension of time makes up the 4 dimension of space-time, which is denoted by mu nu, and which is the first component that we need to understand. 0, 1, 2, 3 is the time and the 3 spatial dimensions. Okay, so we know that Einstein's field equations are, I'm using the word equations because it is not one single equation. It consists of 16 non-linear partial differential equations. So the R mu nu consists of 4, G mu nu consists of another 4, again repetition of G mu nu 4 and T mu nu 4. So total it makes up to 16 equations. So the Einstein field equation that we see is actually comprises of 16 nonlinear partial differential equations which has been coincised into one single equation. So the 6 equations of them which we will see are duplicate, so which makes reduces 16 minus 6 to 10 nonlinear partial differential equations. So this is actually the 16 equations which Einstein's field equations comprises of. So before we go ahead and understand what are the 6 duplicate equations, just a quick revision on a very school level mathematics. We know that if you take a kind of a matrix like 1, 2, 3 and a row and a column of 3 by 3 matrix, then if we transpose this part, this gets into this, right? So the vertical and the horizontal comes the same, and this is what is called a symmetric matrix. Now we know that a metric tensor is a symmetric tensor. Don't worry about those terms, tensor, etc. I will be explaining you one by one. So if you see the metric tensor G mu nu, it actually comprises of 4 by 4, which makes up a kind of a 4 by 4 matrix. But most importantly, these 1, 0 and 0, 1 are the same. 0, 2 and 2, 0 would be the same. 0, 3 and 3, 0 would be the same. So if we write those similar, I would say, components, so what we can do is that 1, 0, 0, 1, this will be equal to this, 0, 2, 2, 0, 0, 3, 3, 0, and so on. So certain factors gets cancelled out, and what we get is G mu nu equals to G mu nu mu, which makes it as a symmetric tensor. So I mean to say we can cancel those things out, and what we get is that this one, the indices of G mu nu and G nu mu would be the same. So that is why metric tensor is a symmetric tensor. So what are the 10 components of the metric tensor? Let us quickly have a look onto that. So we have seen that we have eliminated those, and we have got 1, 2, 3, 4, 7, 9, 10. Yes. So it makes up those 10 components, and remember, all those 10 components are unique to each other. So these are the 10 components of the metric tensor. Okay, the stressenergymomentumtensor, which is denoted by T mu nu, is also symmetric tensor because 1, 0 and 0, 1 gets equals, 0, 2 and 2, 0 is equals, 0, 3 and 3, 0. In this way, if we proceed 0, 1, 1, 0, 0, 2, 2, 0, 0, 3, 3, 0 and so on, then what we get is also T mu nu equals to, T nu mu, which denotes that it is a symmetric tensor. And if we go further, then we see that these 10 components of the stress energy momentum tensor, out of which 6 gets cancelled out, results into these 10 components. And similar to the metric tensor, you will find these components as unique. Okay, so can we summarize the Einstein's field equations, what we have learned till now? So if we write this equation in this way, so the left hand side of the equation actually denotes the space-time curvature as it is determined by the metric G. Now we are soon going to learn and see how this metric G, what it is all about, and how it actually determines the curvature of space-time. But for the time being, let us assume that G is a metric tensor, and the left hand side actually shows the curvature of space-time, which actually in turn shows that this is the geometry of space-time, right? On the right hand side, what we find is the matter energy content of space-time. Now, what do we mean by matter energy content? I will be coming up in this video very soon. But let us, for the time being, understand that entire matter of the universe, starting from electron, proton to black holes, human beings, earth, matter, soil, wood, continents, everything, this entire matter energy content of space-time is been denoted by this. and this is actually denotes the matter movement. So I mean to say that how matter moves is being determined by the right hand side, and most importantly these two are equal. So the geometry of space-time is equal to the matter of movement. So that is why there is a famous saying that matter tells how the geometry curves and so on. So this is actually a kind of a summary to let you know that how we summarize the left hand side and right hand side. So left hand side particularly deals with the curvature of space-time or the geometry of space-time, and the right hand side deals with the matter movement, that is the content of the matter of space-time. Okay, so first we come to the right hand side and we try to understand what is called a stress energy momentum tensor. Now the word tensor actually has been widely used in general relativity. The reason being that tensor, we can call it as an exotic component or a mathematical component which more or less changes with a certain set of rules. I have got separate videos on tensor, but what stress energy momentum tensor comprises, the what tensor is a certain coincide mathematical formulations which adhere to certain principles, which we will soon find out. Okay, so I have written here that curvature equals to matter because you will soon find the reason behind that the curvature of the space-time is actually caused by matter. So the presence of matter curves space-time, right? We know that. So if you put a kind of a famous analogy, a ball or any content on a thin sheet of paper, it actually creates a dent. It creates a curve. So what consists of matter? So we know from the special theory of relativity that this is actually the relativistic mass, and this is actually the total energy of a moving body. I would like to tell you here that this is coming from special theory. I'm not going to explain the derivation and where it comes from the Lorentz factor, but it is basically the relativistic mass. So the mass which is there during the Newton's time has been redefined as relativistic mass, and total energy E is now consists of mc squared, which encounters the speed of light also. So if we consider what consists of matter, we take energy, density, momentum, flow of energy, pressure, and stress. So these six factors comprises of matter. Now just note that these are not the classical definitions of energy density. With the advent of special theory of relativity in 1905 by Dr. Einstein, things have changed. We have redefined all those content into different terms. I will just show you in a glimpse what those are. So the energy momentum tensor in physics describes the local distribution of mass, momentum, and energy. So a tensor, which we will soon discover what it is, actually comprises of things which are local, and it comprises of energy, density, momentum, flow of energy, pressure, and stress. In total, these I would say functions leads to what is called a matter. So this momentum tensor describes, or this mathematical model describes, the distribution of mass, energy, and momentum. Okay, so one by one we will go forward and understand what are the different aspects of stress energy momentum tensor, the way we understood the Einstein field equation. So if I take two dimensions t and x, and if I denote red by energy density, the purple is momentum density, and the green one is the pressure. I will soon explain what is momentum density, but for the time being let us understand this. Then if we can extend further it into 4 dimensions, then this becomes what is called a stress energy momentum tensor. So I'm going step by step. I'm taking the 2-dimension approach and plotting it on a 4-dimension, which makes up the stress energy momentum tensor. Further, as we move, what we find out here is that if we take a 2 dimensions, which is called the momentum density, if you want, you can just go back and have a quick look. The momentum density, which is here in purple, has been plotted here as this momentum density. And in 3 dimension, I have taken length, breadth, and height. So x, y, and the z component, this momentum density, then get plotted. You see this tx now getting plotted as txt and tyt and so on in 3 dimensions. So this is the momentum density. Now in 2-dimension, if we further go and we take this factor, this is called the pressure. So the pressure again in 3-dimension plotted out as x, y, z and x, x, y, y and z, z in 3 dimensions. And there are certain other aspects, t, zx, t, yx, etc., which here we are going to look forward later. So this is the momentum density, this is the pressure. Okay, so the stress energy momentum tensor, something it looks like this, right? Yeah, so it looks like this. So what we found is that this is actually an extension of a classical tensor. Here I would like to tell you that it is called the stress energy tensor or the energy stress tensor. Historically, it is a relativistic extension to the classical stress tensor, hence the name came from. But it should be, I think it should be called the momentum flux tensor, right? Okay, so we go ahead and we try to understand. So this is a relativistic extension, right? Okay. It describes energy and momentum flux. It describes the energy and the momentum flux through space-time, and it gives rise to the gravitational field in general relativity. So this is very, very important. Now, just note that I have just told you that it's an extension of a classical stress tensor of Newtonian mechanics, right? Now, when I tell that it is an extension of classical tensor, if it is a classical tensor, you can see this one, which I have just written. The energy momentum for vector is defined as this. So this is actually written in a vector form. Why in a vector form? Because it has not yet been extended into the relativistic arena. So we are still stuck in between in the classical phenomena in the Newtonian mechanics, where we are defining stress energy momentum tensor in the vector form. Okay, so we see this one, and this is the energy, which is equal to mc squared, later defined by Einstein. Momentum, this is the momentum, right? This is the momentum energy vector, so it is in the x direction, momentum in y direction, momentum in z direction. This entire form, this part, this one in red, is actually written in a vector form. As I told you that we are still stuck in the classical arena, which is the vector form. So we need a tensor form. Now it is still not the right phase in our video to explain why we need a tensor. Let me try to explain at this point of time. As we all know that from special theory of relativity, we are moving into the general theory of relativity, and general relativity deals with arbitrary spaces, curved spaces, bumpy spaces. So we need a mathematical object which, given in any direction with a change of coordinate, the basic rules or the ideas or the the rules of that particular mathematical formulation doesn't change. Because if the coordinates change and the vector changes, then it would become very difficult for mathematicians to discover and further explore the formulation. So we need a tensor. The reason behind is that we need to formulate everything in such a way that in spite of those arbitrary vectors and arbitrary spaces, we still find out the formulations. So here it is. This is what we call the stress energy tensor. We will explain one by one what are the factors. So this part, this red one, is the momentum density. This one is also the momentum density. This one is the energy density, which takes the first position in the stress tensor, stress energy tensor. This one is the shear stress, the blue one. The green one diagonally is the pressure, and this denotes the momentum flux. Just one point I would like to tell you, that here E equal to mc squared, because c squared is the highest, I would say, in terms of the velocity of light. That is why energy density will always find an important position right at the beginning. Because compared to other momentum density and shear stress, etc., the energy or the speed of light is considered to be the maximum. It carries the highest value. So that is why energy density gets at the right at the first position. So in summary, you can read the bottom part, that every part of energy that we think are in some way or the other finding a place in this house. You know, pure energy, rest energy, mass, stress, spin, every not the Spain, I would say the entire arena. So the shear stress, the everything is there in this particular stress tensor. So you see that the formulation or the idea behind creating the stress tensor is to get in a place where we can plug in all the important factors which comprises of a matter. All the important aspects will be there, and with the change of coordinates, as we will see, these things would remain constant, or even if they change, it will change according to a strict rule. Okay, so let us understand what is the meaning of those terms. So first we get what is an energy density. So it is the amount of energy stored in a given system. So it is therefore energy per length cube. We have got energy flux. It is the rate of transfer of energy through surface. So you can imagine something or other. We have read flux in Maxwell's equations or other areas of classical mechanics. So you can understand what is an energy flux. So momentum density, this is the rate of change of momentum flowing through a unit area. You can just imagine it to be a fluid with density of flowing at a velocity of v, something like that. So the units are force per unit area or pressure, something like that. Then we get what is called a momentum flux, that is the rate of change of momentum flowing through a unit, and we have pressure, and we know what is the shear stress. So these are the names of the term. Note that these are classical terms which are, I would say, extended into the relativistic form. So that is how it is. These are the names of these terms which we deal with stress energy tensor. Okay, so we will go now by the components of the stress energy momentum tensor. First, we take the energy density. So energy density, which is responsible for the curvature of space-time. So pressure, I have shown just an icon where you are crushing something with your hand. So pressure also acts as a source of space-time curvature. Then we get the energy flux, right? So a flux is a flow of something per unit time, per unit area. So if, for example, you're considering sunlight through a window, there is an energy flux, which is the amount of energy in the sunlight flowing through the window per second divided by the area of the window. So you can take a nice analogy that energy flow is per unit through the window per second divided by unit area. So these movement of matter actually causes an energy to transport from one place to another. So if I'm moving around from this room to the other, to my lab or some place, then I will try to move, and this movement of matter causes the generation of energy, which will cause eventually a change in the curvature of space-time. So these are the first three units. Then what we are left with is what is a momentum density. So in relativity, actually momentum is a 4-vector like it is Newtonian counterpart, but it had got a 3 spatial components which we have seen, plus a component of the time dimension. So this is the energy and momentum. You see mass flow multiplied by momentum mass, and entirely this energy plus momentum plus pressure and stress actually brings up the entire matter. So the content that you see, this curvy kind of a stuff where I have underlined it in purple and red. So this is actually the energy plus momentum and the pressure and the stress, which comprises of the stress energy different part. Okay, so energy, momentum, pressure and stress, they comprises of T mu nu, which is the stress energy momentum tensor. And remember that this T mu nu comprises of zero divergence. So what do we mean by zero divergence? We all know. So important question is that you can just skip over this equation. I will explain it in later. So it is not energy, not mass, that is the source. It is energy, not mass, I'm so sorry, that is the source of gravity. So the question arises that if is zero divergence of stress energy momentum tensor same as conservation of energy? No, ordinary energy does not vanish, only the covariant divergence vanishes. So this is important. So only the covariant part of this actually vanishes. So this actually should meet with the zero divergence, because I would like to explain to you that the left hand side of the Einstein field equations actually comprises of something which is called Einstein tensor. Okay, for complications purpose, I have skipped that part. So Einstein tensor is zero divergence, which should be equal to stress energy momentum tensor, which is also of zero divergence, because in nature the books should balance, and here also we see that the books balance. So the Einstein's tensor equals to the stress energy tensor, and both have zero divergence. Okay, so we have finally dealt with all those four coordinates I have just mentioned. We have dealt with what is an energy density, what is an energy flux, what is a momentum density, and what is stress tensor, that is a pressure or the shear stress. So all those components along with the stress energy momentum tensor in total comprises of what is called matter and how it causes a change in the space-time curvature. Okay, so we come to the next important part of our video, which is called Ricci curvature tensor. What you're seeing right now at the bottom is one simple equation of Ricci curvature tensor. Now, as you see that the stress energy tensor, Ricci curvature tensor, all these are tensors for the reason that in general relativity, as we change coordinates arbitrarily, it becomes very important that we frame a mathematical formulations which adheres to the formulation rules. Okay, so Ricci curvature tensor measures how a shape is deformed as it moves along the geodesics in the space. Okay, before this okay, fine. So let it be on a kind of an XY curve. So just note very importantly that Ricci curvature is a measure. Okay, a shape is deformed as it moves along. So the immediate question which might be coming in your mind is that how can a shape deform? I mean to say, a shape is a shape, right? An apple or an orange, it is a shape. Now how it gets deformed as it moves along the geodesics in the space, we will soon see that. So geometrically, the Ricci tensor then describes how much this space-time volume changes as you move along the geodesics. So let us see a quick example, a demonstration. So we get a curve coordinates like x and y, and this we get a kind of this kind of coordinates. So if we start with a point somewhere here, and we start with a line, right? We start with this line which travels straight and then curves down, bends down, and ends somewhere here, right? This is a track. Let us just understand it is a track. We get another point, just look at it a little bit below, and this curved path, and it starts around here, it goes around here, and then it curves further. So what we see is that those two tracks which initially started parallel geodesics will begin to deviate due to curved space-time, or sometimes it meets at certain time. So what I am trying to tell is that in the presence of the curvature, these geodesics starts to deviate and the space-time volume starts changing. I will demonstrate more on those. So in space-time, all the different parts of the objects will follow their own geodesics through space-time, which I have just shown those two purple lines. So therefore, if curvature is present, these geodesics may begin deviating from another and the space-time volume will change. It can curl down and meet at some point of time. So physically, this means that the object will get stretched or squeezed in different directions. Here it is getting squeezed, somewhere you will find it is getting stretched. So this squeezing and stretching on the other hand corresponds to the effect of tidal forces, which is simply the result of geodesic deviation and so on. Okay. So here we want to show you something, although this is something we will explain later. So we start actually with the Riemann curvature tensor, which is explained here. And then we go to Ricci curvature tensor. Remember, Ricci curvature tensor is also symmetric. Then we come to Ricci scalar. And then we find that Ricci scalar is a contraction of Ricci tensor, which is a contraction of the Riemann curvature tensor. So you see, Ricci scalar is a contraction of Ricci tensor, and which is a contraction of Riemann curvature tensor. So here it is. Ricci curvature tensor is a contraction of Riemann curvature tensor. So from Riemann we go to Ricci and then come to Ricci scalar. However, we can go from Ricci scalar back to Ricci curvature tensor and Riemann curvature tensor. So right for the time being, we understand that this curvature tensor actually will show us how much an element or a matter deviates or volume changes as it moves along the curved space-time. Here is the Italian famous mathematician Gregorio Ricci curvature, and Ricci curvature tracks down volume change along a geodesic, which means how volume grow and shrink. We will soon see how it is. Depending on the curvature, Ricci curvature R shows the change in volume in either of the following way. It can be static. You can say that the volume change, there is no volume change. It can be growing, that is the volume is growing, and it can be decreasing, that is it's shrinking in size. So independently, the Italian mathematician Ricci curvature, much earlier to Einstein's formulation of relativity, found this Ricci curvature, which was used by Einstein later in his magnum opus General Theory of Relativity, or GTR, so that it helps to calculate those. Okay, now this is something very, very important which I would like to explain to our viewers. The change of volume under linear transformation in orthogonal and non-orthogonal plane. Now, let us try to understand in this way that when we are dealing with things which are in the Euclidean plane, things move pretty straightforward, right? I mean to say they move along in a straight line. So that is the orthogonal plane, that is when it is 90 degrees. And also what will happen when it moves into non-orthogonal plane, and that is the basic challenge. So let us start with the basic orthogonal plane, where we are primarily dealing with Euclidean space. Let us understand. Now this is something which we have done in school days, using determinant to calculate the area of a parallelogram. So this is a parallelogram, and this is how we calculate. If P be a parallelogram and V and W are the vector, then this is we calculate it by plus minus area in using the determinant value. Okay. So now the question is that what do we mean by volume growth? Now I'm going to show you this volume growth in terms of orthogonal plane so that it becomes easier. Now if I get a kind of a linear map which is transforming n-dimensional space to m-dimensional, then there is a one-dimensional linear transformation. So the one-dimensional linear transformation, as you see, the blue one, 0, 1, gets a little bit extended to x prime to 0 to 3, right? So this is the T that maps the interval 0, 1 and 0, 3. So the determinant of the matrix associated with T is 3, right? From the left hand side you see 0, 1, which has grown in size by 0, 3. So it stretches the object so that their length is increased by a factor of 3. 3 times it has increased, right? So this is a kind of a 2D linear transformation, and we can do this by A, B, C, D and X, Y. Okay. So just to tell you that this is what do we just starting that in one-dimensional linear transformation, the determinant of the matrix T has grown by 3. So a stretching of two-dimensional linear transformation. Now what do we mean is that, see this figure, what has happened is that this blue, yellow, green and red, when it is taken the matrix form of minus 2, 0, 0, minus 2, the top one which is showing that arrow, so it is getting transformed. So what it happens that it rotates the objects by pi radians and stretches to increase the area factor by 4, right? So this is what is called stretching two-dimensional linear transformation. I hope things are clear. So from one dimension we saw the determinant which increased from 0 to 4. This is stretching of two-dimensional linear transformation from which is rotated. Okay, now let us see that how a flipping happens. So we just flip this same coordinates into this, and you see that T doubles the area and the orientation is also reversed, right? So the blue which is on the right hand side suddenly turns to the the yellow which is on the right hand side suddenly turns to the yellow on the left hand side. The blue which is on the left hand side goes to the right hand side. The green which is on the below right hand side suddenly moves to the left hand side. So what happens is that the area not only is doubling, but the orientation is also changing when we are plotting it with minus 1, 3 kind of a matrix. Okay, a three-dimensional linear transformation, if I take a kind of a matrix A11, A12, 13 and so on, which is right in front of the screen. So this is a kind of a cube, I would say, or anything that you might call. You see here what happens is that the determinant is increased by a factor of 12, and the t is rotated the cube and stretched it into a parallelepiped. So the cube is now a parallelepiped, and it has increased the volume by 12. So the expansion of volume of t is reflected by the fact that the determinant of A is 12. The basic idea of showing you a 1 dimension, 2 dimension, 3 dimension linear transformation, this is how, when we are using matrix transformation, the volume is changing, the size is increasing, and things are getting flip-flopped in either way, right? So I hope that this is clear, that what do we mean by volume growth. Although this is not a volume, it's a change in terms of orientation and size. Okay, so what we have learned is that the transformations determinant, that means once we use the determinant of matrix, specifies as the volume of an object changes. If the determinant is 1, the volume is preserved. If it is negative, then it is a mirroring or a kind of a reverse space order. When orthogonal transforms are applied, that is, we are keeping it an orthogonal rotation translation, then the shape is preserved. Now here is something important. By the word preservation, what I'm trying to tell is that if you have gone through my video on smooth manifold, Riemannian manifold, diffeomorphism, there is a concept that how we preserve the size. Why preservation is important? Because if it gets diffused, it will be difficult for us to do the calculation. And this preservation of volume by a function or its negative function is what is called diffeomorphism. You can see my video. This is not the right time to talk, I know, but diffeomorphism, how it is different from homeomorphism, is a factor which speaks about preservation. So here the cube is now stretched into kind of a parallelepiped. As you can see, this sphere, which is marked in blue, has now become an oblate spheroid. So these are the changes, these are the examples, illustrations, which shows that how a volume changes, right? And we will soon see that this volume change, how it is encountered in space-time. So the 1D to 2D and then 3D, and this is how the change in volume affects us. Okay, so all these were on the top, as you see, these are on orthonormal basis. But what we want is a non-orthonormal basis rather than arbitrary, bumpy, curvy system, right? Because it is a general relativity where we are generalizing everything, right? Okay, so here we have to introduce a concept called volume element, which is, or a volume form, which is denoted by omega. And I would be skipping the complex mathematical equation for this, because this is not the right time or the right place to explain volume form. But just note one important thing, that the volume form is a special differential form defined on an oriented Riemannian manifolds, and which introduces a natural concept of measure on the manifold, and this is called, we need a tensor. So for non-orthonormal basis, we need something called a volume element or volume form, which is denoted by the omega sign. And we are not going to encounter the mathematical part, but from orthonormal, if you move to non-orthonormal, what we get is a volume element or a volume form. Okay, so now what we see is that how do we move along the geodesic? That means we know right now what is Einstein field equation, what are the factors that determines the curvature. We have seen that stressenergymomentumtensor causes the curvature in its different form. We have also seen that how a volume element or an object changes. Now is the time that how it moves the volume change along the geodesic. So the change in volume geodesic along the sphere. So for example, this is a sphere, and these are the people, okay, the purple and the green ones. As you see, they move along the geodesic. So it is assumed, it can be assumed hypothetically that they meet at a certain point. Right, you see here, they are meeting at the poles. Now, if you get a kind of a sphere like this, and we get a kind of a arrow like this, I mean, see, if you're moving along the geodesics, So here is a sphere, and it further changes, shrinks down, it shrinks down further, shrinks down further, and it shrinks down further. Right. So just on the left hand side, as I have shown an analogy that people, when they're traveling, they meet at a certain point on the pole. So if you're moving along the geodesic or on the sphere in this way, which is a positive curvature, I would say, so the spheres are decreasing in size, and this is determined by this r mu nu. So the ball shrinks in size as it moves along the geodesic, which, as I was telling you, it means it is a positive curvature. So this is actually what we mean by change in volume as it moves along the sphere. So let us see a few more examples. So this is something which is a flat one, right? And I move this object to this, right? You can see again this. So what has happened to the volume? Nothing. So it is a straight geodesic, and the Ricci value is 0. We get a kind of a converging geodesics. We just saw in the sphere. So here is the box. It further shrinks, it further shrinks, it further shrinks, and what happens to the value? It is greater than 0. So I can say from the volume which started, it reduces 1/4 in the size, as it is a converging geodesic. What is the third case? That these are the spreading geodesics, right? So these are the diverging geodesics, and the size of the volume increases, and further increases, almost increases to 4 times, right? And the Ricci curvature, or the Ricci part, is less than 0 because the volume increases, right? So what does the Ricci scalar now denotes? So the Ricci scalar, we got the next part, that is this R1. So the Ricci scalar actually keeps track how the size of a ball deviates from a standard Euclidean space. So what do I mean by this is that, for example, if I've got a flat circle which has not yet taken the form of a ball because it is in Euclidean space, right? So I want to track how the size of a ball deviates. So now it becomes a disk, and then it becomes a sphere. So I'm trying to put in this disk inside the sphere, and you will see this one, it shows that the area that fits in sphere is more than it fits in flat space. Right, so the disk now is fitting on the sphere, the area under this curved dotted line is more. So this is how we keep track of the size of a ball, and this is exactly what Ricci scalar does. We'll give you further examples of Ricci scalar. So this is a circle which has got pi r squared. Now I'm trying to fit in this circle along this black area, so the area increases. The surface increases as the ball gets smaller. I'm going to say the ball is getting smaller, it is squeezing. I'm trying to fit things in, and finally you will see the further surface area increases by 2 pi r squared. So the final conclusion is that as the circle becomes shorter, we can fit in more area. Hence we can say that we can fit a large amount of area in a small boundary. And how much this area is fitting, this is exactly what Ricci scalar measures. So you see the circle, it's fitting in the second place, in the third and the fourth one. So we are trying to, the circle is becoming shorter and it is getting into more area. So this is what Ricci scalar does. So here is another analogy. So in the bottom you see Ricci is 0. Second, it is more area, and then it is less area in case of this kind of a curve, because this one is 0, this is more, this one is 0, and this is got you can call it what as an parabola, hyperboloid, if I'm not making a mistake. You can correct me, right? So this is the less area part. Okay, so what are the geodesic deviations that we see? So in case of a flat squared one, no increase in volume. We have seen the animation. In the kind of a converging geodesic, the volume increases, as we have seen that it starts from here and then. And in case of a kind of a sphere in a saddle, the volume actually decreases. So it goes like this. It's difficult to show in here. The volume, the volume decreases and then this volume increases. So these are the geodesic deviations. Okay, so now finally we would like to explain this Ricci. This is the Ricci tensor part. It has got 2 lower indices. Don't go by what those indices means. It will be further explaining those things. I will make a separate video on Ricci curvature with each and every element. This is equivalent to this one, Riemann curvature tensor. Okay, and the Ricci curvature is definitely a contraction of the first and third index of Riemann tensor. And this is the first indices, C, and this is the third indices, first and third, right? So you see this has been contracted. That means it has not yet been shown, right? The Ricci tensor, just we have written A and B, we have ignored C. So each and every component of the Ricci tensor, that means is a multiple components of the Riemann tensor, which is this. So R11 multiplied by R101, 111, 121, 131, and so on. And the top changes from 0, 1, 2, 3, and so on. So each component of the Ricci tensor is the sum of the multiple components of the Riemann tensor. So this more or less clears our idea of geodesic deviations, how things are moving. Okay, so what we do is that now we come to the most important part, that what is a metric tensor. Remember that this tensor actually dominates the entire idea of general theory of relativity. So you can look into my video, but I will just give you a very quick idea. What do we mean by tensor and why do we use that? Okay, so metric tensor, we start with this part. So it comprises of two words. One is metric, the second one is called tensor. So what do we mean by metric? So in general, what do we mean is metric means a measurement or a meter. So either we are measuring success, height, length, breadth, whatever we are measuring, it is a kind of a metric. So we measure it in terms of meter. Now tensor, yeah, these are mathematical objects or an array of components. So I will just explain to you. So between this metric and tensor, there is a relationship. So there's a funny figure where this person is thinking that what would be the relation between metric and tensor. Now here is something very important which I would like to tell you. Most of the internet stuffs or other things that you read in, they give a kind of a notion that tensors are generalization of vectors and matrices. Absolutely not. Absolutely not. Now, if I may tell you that vanilla ice cream is a generalization of chocolate ice cream. So what it happens is that it gives a kind of a, I would say, a very easy way out to understand that yes, vanilla ice cream, if I understand, is a generalization. But if I say vanilla ice cream is a generalization of the family which is called dessert, then it will be difficult for somebody to understand, right? So tensors are definitely not generalizations of vectors and matrices, just like vectors when we denote by arrow left and right, and we are doing vector multiplication and addition using the tip to tail method. So these are not vectors and not arrows. So what we can say that tensors are, coincide mathematical framework. We can say they transform, obey certain rules, or I can say the tensors are multilinear maps between vector spaces and members of their own vector space. Tensor is a mathematical object that can be used to describe physical properties like scalar and vector, which are often used in physical and engineering applications. So it's a quick note. I just thought because most of the students they get confused with this wrong notion. So it is not a generalization. It is a linear map, or let us think that it obeys transformation rules and they have a coincide mathematical framework. Yeah, so it is a multilinear map which I was just telling. So let us now we go forward and try to find out the relation between metric, which is a term for measurement, and tensor, a kind of a mathematical work which obeys certain rules. Okay, so the question lies that why do we need a metric tensor? In general relativity, why do we need a metric tensor? Now, the basic reason is that if you see this kind of a picture where Einstein is sitting and on his left hand side his famous friend Marcel Grossman, who has been a classmate in Zurich. Now, I hope you don't take it wrong that Einstein had no idea about what is called differential geometry or tensor analysis. He has been independently trying to develop special theory and later general theory. It was Marcel Grossman, and there are a lot of examples. I have shown this in my video, The Architects of General Relativity, where you can see that these people, Marcel Grossman has actually mentored and taught Albert Einstein that, come on, my dear friend, this is what is differential geometry, this is what is a tensor, and you must use tensor in order to use the framework of general relativity. So this has been introduced by Marcel Grossman, his friend Michel Bessot. So these are the two distinguished mathematicians. The right hand side, the person on the hat with a long mustache is called Gregorio Ricci Curvastro, and the Italian mathematician Tullio Levi-Civita. So they independently developed the concept of differential geometry and tensor, thereby used by in mathematics by Albert Einstein. So when we take a kind of a flat surface like this, right, and we try to plot a straight line, so it goes this, no problem, right? And in case that we come out with a curved surface, this line behaves and it takes a curved line, something like this. So if I take a natural numbers 1 to 3 going up to n, then what a tensor actually does is that it creates a multi-dimensional array. Now here is something which we call the basis of a vector, right? So we got our xy coordinate, and the basis of vector sometimes changes in this way, it changes in this way, and it changes in this way. So in case, because as I have been telling repeatedly, that general relativity deals with arbitrary, bumpy, crazy kind of a curvy surfaces. So if the basis of the vectors is changing in this way, the tensor also changes in this way. So that is why I show this arrow. The tensor also changes in this way, but with a certain mathematical framework with certain set of rules. So that is the reason we are using tensor. We'll find out more. So if we get a kind of a surface like this with points 3, 2 and 5, 6, then we can use the pure old formula of using the distance. Then we calculate this one, which gives to this approximately 4.472. So this is the good old Pythagorean theorem, right? We are using in order to calculate distance in the Euclidean Cartesian coordinates. Now if you get a kind of a surface like this, what happens is that this will no longer be valued. It won't work out in this kind of a curved surface. So what we need is a metric tensor which would help to calculate the distance between 2 points. So it defines and compute lengths of curves on manifold. Don't worry, we will be explaining more about manifold. It is an infinitesimal distance on the manifold. It calculates, and it calculates tangent vectors. So till now what we know is that metric tensor is a kind of a mathematical framework where we cannot use the Pythagorean theorem, but we can use something else which will help us to compute length of curves on a manifold. So if we get this kind of a curve and we get a point, then we do what is called tangent vectors. Those who are, I mean to say, you know what is a tangent vector. So we get a circle, we further get a tangent vector which just kisses the red point. And if we get a line like this, so we calculate and goes on adding up these tangent vectors, right? So why we are using tangent vectors? Because general relativity is full of curvature. They are full of curvature in this particular subject. So we have this kind of curved surfaces. So we need tangent vectors. Why? It will come true. So just remember, this is a way we calculate the tangent vector. So we have something, just to give you a basic idea, which is called a tangent bundle, which collects or assembles all the tangent vectors. So if this is a kind of a manifold, or let us say it is a surface which is M, and these are it is a differentiable manifold, and these are the lines which are going up, and these are all the different collections. So these are what is called tangent bundle, right? I mean to say, it is a bundle, it's a collection of tangent vectors. M is a differentiable manifold. Don't worry about this term. We will soon find out what is a differentiable manifold. So we got tangent vectors, then we got tangent bundle. We need one more thing. So this is a kind of a surface, and you can see this once it is why I call differential manifold, because all these infinitesimal small distances on this surface can be used. Yes, differential or differentiable manifold is a topological manifold which has a differentiable structure. Differentiable structure means where we can use dy and dx, and we can use calculus to calculate the distances. So a differentiable structure on a set M makes into an n-dimensional differential manifold on which you can do differential calculus. So I hope the picture is becoming clear, right? So starting from Einstein field equations, stress tensor, and now we are measuring distances, metric tensor, and we got a differentiable structure in general relativity, because general relativity deals with arbitrary structures. So until we differentiate, how can we calculate distances, right? So this is what is called a differentiable manifold or a differentiable structure. So this is M, and this is something called tangent bundle. So if it is a differentiable manifold, it assembles and collects all the vectors in M. So it is a disjoint union technically of the tangent spaces. What is a tangent space? So we got a surface, something like this. We got a point, right? And this is just the point which is X. And I have got two, vectors which are pointing this way. And this is a manifold. So the set of all tangent vectors at a point X form a tangent space. That means the possible lines which are going through, they will form a tangent space. So here is another example. So you can see these lines are just kissing through the point, right? So this is one, and this is one, just kissing through the point. And this is the tangent space which forms, right? This one. So sorry, this one is the tangent space. So from tangent vectors, we got tangent bundles and we got tangent space. Why we are doing all those things is that this metric tensor is one object where all those tangent vectors are pushing inside, they are being processed, and what it results is a real number scalar. This is GVW. So a metric tensor, I can say it is a generalization of the property of Euclidean space. If a manifold is equipped with positive definite metric tensor, it is called a Riemannian manifold. We will explore what is a Riemannian manifold. On a Riemannian manifold, the curve connecting two points that is the smallest length we have seen is called a geodesic. So this is more or less 1, 2, 3 important points of a metric tensor. Well, this is not a Shakespeare's play measure for measure. This is just another example to give you a very easy understanding of a metric tensor. Let us assume this dollar to be a kind of a currency, a standard. And we have India, which gives a value of 73.52 INR in terms of the Japanese yen and the Thai baht. So all these are measurements, right? All these are, metric tensors. So these are actually giving birth to the concept of metric tensor. So the value of dollar, depending on different countries, their currencies, their food style, their living style, their economy changes. So it is also a kind of a metric. Further, if I am standing here and this is my sweet home, then what I can do is that I can take a straight path reaching my home, and I name it as G equals to D Euclid, because we are using a Euclidean formula just to go straight. Now if I take a taxi or a cab and I've got a pond in between my house, I will take a straight different path reaching here, right? And this is called the metric of a taxi, and the other one is the metric of a Euclid. So what is happening out here is that both of these are taking the shortest distance, but both of them are different in terms of, I would say, measurements. One is Euclidean measurement, one is a different kind of a measurement, the metric of a taxi and the metric of a Euclid. Just to give you an idea that what actually we are dealing with. So now what we do is that we will use this metric and we will see that how in the curved space-time things are behaving. So we got 2 points and we want to measure the distance. So we call 1,000 years back, maybe 3,000, 2,000 years back, the ancient Ionian the great Euclid, and we use his formula to calculate in this way. Remember, we are using ds squared. That means here we are trying to measure what is called a differential distance. Yeah, so we are measuring the differential distance. Now, if we take a kind of a crazy curvilinear coordinates like this, and we get two red points, and here is a line. How we are going to measure the distance of these two lines? We cannot use this one. We can use a kind of a formula. It is a kind of a formula which takes the shape of this. Okay, we are not using Pythagorean theorem. We are using this. This is a kind of a quadratic equation which takes the form of 4x squared plus 2x plus 3y, something like this. And this dx and dy, very important in the equation. It denotes that these d are not perpendicular or non-orthogonal to each other. They are not orthogonal to each other because it is a curved space, and we deal with different types of curvatures. Okay, and G actually denotes the amount of spread. Now, what do we mean by amount of spread? Okay, so here I will say that these are the three lines which you can see, and this and there are other three lines, 1, 2, 3, 4. So what it measures is that if you see the distance between these right hand side is much more wider, and this one is much more dense. So this is a loose one and this is the dense one, right? So this G11, G12, G22, these which we look at it. So for example, if I'm located here where the density of these lines, I would say the curvature is less, then it depends. G measures where we are. That means how much curved it is, how much loose it is. We'll soon explore it in a different kind of for illustration. So this is what G actually denotes in a metric tensor, where we are and what is dense and what is loose in terms of curvature. So this G denotes what is called the metric. So this denotes what is a metric. Okay. Now, using that dense and loose analogy, we will use another analogy which is called a rubber sheet analogy, which is quite common in internet and other explanations of classroom. So if we get a kind of a rubber sheet like this, and this is the line which is moving, then we can use, again we are using differential distance, we can use this formula. If the rubber sheet extends, stretches in this pattern, then what we do is that the x and y, we calculate the formula using this. ds squared equal to 2 times and the dy square remains the same, right? Then if we further extend it, this one and this one, they extend further, and we use 2 dx squared plus 2 dy squared. So the basic idea of using rubber sheet analogy is to let you know that once the distance is increasing, but mind it, this is in Euclidean space, right? We can twice or thrice or do whatever in terms, but we are still using the Pythagorean theorem. So we can use the Pythagorean theorem in order to calculate the stretching information. And if you right now remember exactly this is what we said in 1D or 2D linear transformation, how the volume changes, right? So you can now make a link between those two. Okay, so we get a kind of a stretched path. Okay, this is a surface. Let us say this is a surface of this map, which is a stretched one. And I draw a line which curves like this, right? Now, if we get a kind of a coordinate shapes which are something like this, then we can use those points. Then what we get is this one which we have shown to calculate the distance, or this one to calculate the distance. So dx and dy shows that it is not perpendicular to each other. And what we can also see that the unstretched information, now this is something you can check out in my video in metric tensor where I have explained the derivation of 0, 1 and 1, 0. Anyway, so in a Euclidean flat space, we can get the values of the metric tensor as 1, 0 and 0, 1. So we can get this unstretched information using the differential distance formula, and this G1 and G1122, these values are used to calculate the stretching information. So that means in an unstretched or a rather flat space, the values are 1, 0 and 0, 1 if we plot it in a matrix. But whenever we are getting under kind of a stretched information or a stretched plane, then these information stretches, right? So G actually comprises of the stretching information. So this one is expanded into this. So this tensor actually stores all those informations which are required for these coordinates in order to measure those purple line or the distances, right? And this is the how much and in which direction space-time is stretched. That is the measure of metric tensor. That is why it is used in general relativity, because we really want to understand the measurement and the direction in which matters spreads out. So for tensor, we got a rank 0 tensor, rank 2, rank 1. And in case of rank 3, now I have not mentioned here, Einstein used rank 4 tensor, right? 4 multiplied by 4 results in 16. And that is the reason it is called 16 partial nonlinear partial differential equations, which I showed can be reduced to 10 by cancelling out those common factors. So this is a rank 4 tensor where length, breadth, height and time is being used. It is pretty clear that this tensor actually stores information how much and in which direction the space-time is stretched and how we can use this formula to plot it. Now we will come to an important concept which is called mapping. Now I will just explain you what it is. Let us take a sphere and let us take a line around it. Arbitrary, right? I magnify this sphere into a bigger sphere and I use the same stretching chart or the stretched map. This is the unstretched one. I put it over here. So the unstretched map, when it is put on a stretched map, it looks something like this. And again I put it and again I put it. The reason behind is that when I plot lines further, this goes like this, right? When I plot lines over here, I get a stretched information. So from the unstretched component, I can use differential geometry or differentiation in order to calculate the unstretched information, and then I can plot it in the stretched information. You see the beauty of general relativity. So the differential manifold that we saw is required in order to use differential calculus to calculate the distance. And what measures the distance? The metric tensor measures the distance. So we can compute in this way any distance between any kind of a curved, complex, any kinds of a manifold. So we take this unstretched information, we patch it over this sphere or the curved manifold, and then we take it out, and then with the stretched information we try to calculate the G part, which contains the stretched information of space-time, and then we try to find out the distance. So this is what is called a mapping. So we get this kind of a formula through which we can derive. So what we can say, you can read it. I know if we know the stretching information of those complex manifolds, we can use the distance between those points. We can use the entire stretching information stored in the metric, and the metric tensor helps us to understand and measure the tensor itself, which is formed in nice coincide mathematical framework which obeys certain rules. So 1, 2, 3, these are the most important part which we reached till now, that how these stretching informations are being stored in metric tensor and how do we measure it. So the question is that we learnt about metric tensor, but how does it help? I mean to say, what will it come to use? So let us take Jupiter, Earth and Mercury. So we know that Jupiter is a heavy fat boy, right? And the curvature is more. Here you see the curvature is more. In case of curvature is more. So obviously G, this is not that G, this is the acceleration due to gravity, and the weight is quite some, right? The Earth, the dent is little bit less because the curvature here is less, and that is why the weight, and in terms of I would say G, it is less. Mercury, being a little boy, it has got a kind of a lesser curvature. The curvature is less, so it got this value. So I mean to say, this actually helps in calculating the curvature, satellites, GPS, positioning, mapping, everything. So until and unless we really know the stretching information, how and where it is stored, it is difficult for us really to measure, understand the curvature. So this metric tensor measures all those, and I have demonstrated that it helps in measuring the curvature just as it is in astronomy or astrophysics. So we get this kind of curves, we get this and this. So we actually does this using differential geometry. I've got a series, few lectures on differential geometry. So differential geometry helps to calculate those distances, which further moves into manifolds, and it finally encounters into general relativity. So this is a kind of a roadmap how we are proceeding with the general relativity part. So we can tell that metric tensor is actually a way of measuring. Okay, so now we just understood that this M is a manifold and it stretches, and we got the information. So first of all, let us understand that what is manifold in general relativity. So manifold is actually comprises of two words, many and fold. And if you see the original, it comes from Anglian and Anglo-Saxon and Proto-Germanic, Middle Dutch. And the fold words also comes from Old English, field, falder, Proto-Germanic, etc. So it actually comprises of two words, many and fold. And ultimately what it means is this one. So these are different shapes, right? And it actually shows that manifold is something which has got numerous different parts. It consists of different kinds of combinations. It has got many different forms, and it is a collection of points, a kind of a set, such as those of topologically closed surface, a whole composed of different elements. And even I found it that it says that it comprises of several copies as with carbon paper. So anyway, we found that manifold, it comprises of different kind of features. So can we just frame it in a simple manner? So we need to find out that who actually discovered or coined the term manifold. It is this great mathematician Bernhard Riemann. He was the first to do extensive work generalizing the idea of a surface to a higher dimension. So the name manifold comes from the Riemann's original German term, which is this. I won't dare to pronounce. So it is later, it is called manifoldness, which the famous William Kingdon Clifford transferred it. So, So in his Göttingen inaugural lecture, Riemann described the set of all possible values of a variable with certain constraints. And because a variable can have many values, it distinguished between those two. So this is the continuous manifoldness and discontinuous manifoldness, whether the values do change it or not. Now remember, the time that we are talking about Bernhard Riemann addressing to the Göttingen lecture, people were not matured enough to get understand what manifold is. So it was severely, I won't say criticized, but it was not accepted. So as continuous examples, Riemann refers not only to the colors and the locations of the space, but also the possible shapes. So let's look forward. This is the great revolutionary book of Bernhard Riemann, which was on the hypothesis which lie at the basis of the geometry. It's the English translation by William Kingdon Clifford. We all know that the Clifford algebra is named after him. So this is the name, this is the book, and which I underlined that, continuous or discrete manifoldness, etc. So, so Riemann sketched this route and was to become general set theory, which is called discrete manifold, to topology, continuous manifold. So these are a few important points which you can note. This paper gave birth to the concept of manifold, and Riemann's intuitive notion of a manifold involved into what is today called a Riemannian manifold, very important in general relativity, and Riemannian surfaces named after Bernhard Riemann. So a kind of a quick note on the historical aspect that how the manifold term was given birth to by Bernhard Riemann. So manifolds are objects in topological space which deals with numerous shapes and form that are bent, right? and every point on a manifold has a small area which looks like a Euclidean. This is very important. So I have got a separate video on manifold, Riemannian manifold, and different types of manifold in the differential geometry playlist. You can have a look onto that. So how can we visualize a manifold? This is a sphere, this is a person standing, and it moves from one point to another, right? From here to here, and further here, and here, and here. So different ways the person is moving, right? And now we have got a manifold. We know what is a manifold, right? So this is a manifold. The same person now starts moving from here to here, to here, to here, and so on. So what it happens is that the movement along a sphere is now locally, I would say, it is looking like a Euclidean space near each point, right? So if I am moving from this room to the other, I won't be able to see the global picture. That is, I am on a sphere and moving in a curvature on a geodesic. I will assume that I'm moving straight, or I'm moving as per the Euclidean plane. So a manifold is something which should be locally resembling to a Euclidean space near each point. This is global and this is local. Right, so it is a topological space that is locally Euclidean. So you can see this one, it is a points in the neighborhood, so that it can be used x1, x2, x3 and so on up to xn. So Euclidean or Cartesian space is that space of all real numbers denoted by Rn, and a locally Euclidean space, it is topological space that looks like Rn. Simple, very simple. So we take a manifold, we define a manifold when those neighboring points etc. are real numbers, and it looks something locally like Euclidean plane. This one is the local and this one is the Euclidean. Okay, so we got a similar example. We have got an Earth. It is two-dimensional R3 because in R3, because we live in a three-dimensional space. This is the one, so we can specify point. And in general, any object that is nearly flat on small cases is a manifold. This is an example with our Earth. Okay, so we go ahead and we try to analyze a manifold. We first take the sphere and we get a kind of a positive curvature. Now you see, whenever now you're trying to imagine a manifold, you can now understand that this is a kind of a movement of that ball along the geodesics. So it is shrinking and stuffs like that, right? So here it has got no manifold, no curvature. So you can say the Ricci curvature now is 0. That is the beauty of learning, right? And this one is negative curvature. So we take a kind of a surface and we break it into small further pieces. We use the differential calculus and we can apply the calculus on the manifold. This is the reason we call it a differential manifold and applying the rules of calculus. That is how we analyze a manifold. So we take the manifold part, we further subdivide it using calculus, and it locally looks like Euclidean. So we can also tell that these small yellow surfaces actually denotes a real number on Rn, and this is what is called, it is, I can say a manifold is a space that is locally isomorphic to a Cartesian space, which is an Rn. So these people who are moving now, it is locally isomorphic, more or less similar to the Cartesian space in Rn. In general relativity, you will often come across photographs like this, this and this. You have seen it many times, I'm sure. So what does this mean actually? I would like to show you the actual meaning of this kind of a surface. So all these small boxes, these are differentiable manifold. So until we differentiate it, we won't be able to understand the space-time curvature. These are the curves. Now you understand what is those curves, how Ricci scalar and GT tensor measures it, how metric tensor measures how it is spread out, right? So this is the curvature. These are the lines which are a little bit dense, right? So here you stand and the lines are denser. These are the lines which are a little bit loose, right? Where you're standing here and the lines are loose. And this is the geodesic which is moving along, and you're moving along the geodesic path. And the metric tensor actually measures everything. So it is a kind of a one single photograph or a demonstration which explains general relativity, everything together. The curvature, the geodesic path, the differentiable manifold, and the metric tensor measuring the density or the where you are located. So we almost have come to the end of the video, and we will try to understand what is a Riemannian manifold, because this is central to the idea of general relativity. So Riemannian manifold, we can say that, is a real differentiable manifolds where each tangent space is equipped with an inner product, the Riemannian metric, that is defined as the shortest length from one point to another. Now, we will go forward with the definition, don't worry. So first we need to understand what is real, that is a real number. What do we mean by differentiable? Tangent space we already know, and what is a Riemannian metric? So we will skip apart real and tangent space, we already know. We will go forward in understanding differentiable and Riemannian metric, so it completes the understanding of Riemannian manifold. So what is a differential manifold? To be very honest, we have already looked into that. So I can just give you a simple definition. So differential manifold is where you can apply calculus. Simple. It is a differential manifold is a generalization. We can use the Euclidean space to higher dimension, which is called a smooth surface. I've got a complete entire video on smooth surface. You can look into differential geometry. And differentiable manifold is locally homeomorphic to Euclidean space, such that the gluing, which relates to Euclidean local charts, and others the differentiable functions for a fixed degree of differentiability. I won't explain the third part, because again we have to go towards what is homeomorphism, diffeomorphism, charts, etc. So it is something where we can apply calculus. So I would like to show you mathematically simple demonstration how it looks like. We take a kind of a manifold, we map it over here, and there is a continuous map phi, this one, and there's a chart around the point x of m. If you don't understand what is a chart is something kind of an approximation. It's like a page of an atlas. It gives you a flat approximation of a small piece, and an atlas comprises of individual charts, right? So again, as you see that we are trying to map something on a flat space. So that is a chart. Now we take this illustration, and these are the two functions that we use, the phi and the psi, right? Rounded in, this is in red. And this is where the chart intersects the point I would like to show you. You see this little one, the black one, this is where the chart intersects. And we take another photograph where we map this one here. Again, I map this one here, right? So the common intersection point is mapped over here, and then we use a transition map. So I'm not going to explain what is a transition map, but we use a transition map. And remember, this one is not a dot product, it's a composite function. So all in all, it is a map between Euclidean spaces formed by composition. So we take two manifolds and we make it, on a chart where the point intersects, and we draw a transition map. This is more or less what is called a differential manifold. This is a clearer picture, which we have cited the site where I've taken it, and you can understand this is going here and here. Okay, so a Riemannian metric of a family is a family of smoothly varying inner products on the tangent spaces, right? And these are used to measure infinitesimal objects, to measure the distances. So if Sm be a smooth manifold, a Riemannian metric or G on S is a smooth family of inner products on M. We take G as this one, right? So the smoothness condition on G refers to this. So it must be smooth for every locally defined smooth vector fields. So this is a positive definite symmetric bilinear form. And remember that we go further. So the smoothness of G depends on this, right? The smoothness of G depends on P being a member of M and so on, which leads to it must be smooth for every locally defined smooth vector fields of X and Y and M. So just remember that Riemannian metric manifold is a pair where M is a differentiable manifold So one part is this. It is a differential manifold. You know what is a differential manifold by now. And G is the Riemannian metric on M, this one. So later, as you will see, that often to simplify the notation and refer to M as a Riemannian manifold. So we just refer M. So the metric is involved in it. I would say it is implicit. We don't need to mention those. So what we can tell is that if we take a V as a real vector space, right? So if you take V as a real vector space, then we can select, so this is a demonstration of a vector space. So we can just select an inner product. I'm not given any value A, B or B, Y. So once an inner product is chosen, one automatically gets a norm, right? By defining V square. And consequently, we can also get a distance function on D by using V minus W, the distance between 2 points. So here is M, which is a differentiable manifold, and its tangent spaces, this one, T sub Tm are vector spaces. So we choose an inner product on each tangent space Tpm, and such a choice is called Riemannian metric. So we choose this one, and what we get is a Riemannian metric M. And a Riemannian metric on M gives rise to this distance function on M. Okay, so I will further explain what do I mean by this in the next part. So in simple words, what we can say, a Riemannian metric is a way of measurement. It is a family of smooth inner products on the tangent spaces, and it helps us to measure local notions like angle, length, curves. So that means we are using the manifold to take it into a local part, and then we using Riemannian metric to calculate the length, etc., which will be able to calculate the measurement of a matter moving across general relativity spacetime curvature. So we know that inner product is the generalization of the dot product. It is a way in which we can multiply vectors together, right? So if I take this kind of a manifold M, and for example, we need to multiply multiple vectors on that manifold. Why we need multiple vectors? Because we are moving in different directions. The matter, which we saw it in stressenergymomentumtensor, is moving in different directions. So it takes this form. Move in different directions. It is marked by V. So our target is to equip the tangent space, the entire space, with the inner product so that the inner product varies smoothly. Why smoothly? Because if it is not varying smoothly, it would be difficult for us to calculate. So these are the 2 points, and we get a curved line, a red one as this, and then I have taken it in ResearchGate. This is the photograph which shows this is the tangent vector, this is the geodesic which you see, and this is the real geodesic. Okay, so if it is still not clear, let me know in the comment box, because this is important. So if we want to multiply multiple vectors together, we have to equip the tangent space with inner product, and this is exactly what the Riemannian metric or Riemannian metric does. That if you need to multiply, we need to equip it, and this is how we do it. Okay, so such a long video finally coming to an end. So what do we stand right now? So first we understood all about Einstein's field equations, the different components. Then we understood what causes the curvature of space-time, that is the matter, what comprises of matter, stress, energy, momentum, tensor. How do we measure if things change in volume? So we learned first with a 1D, 2D linear transformation, and then the 3D linear transformation, and in non-orthogonal plane, we use something which is called a volume form. Then we learned how it changes in orthogonal and orthogonal plane. We also learned how matter moves in spaces in geodesics, taking a 0, positive and a negative curvature. We also learned how do we measure our curvature, that is the metric tensor. We learned it thoroughly, what is metric tensor all about. If in case you want to understand the real derivation of metric tensor, go to my video in general relativity playlist, which is called metric tensor. You will get a further mathematical understanding. What is a manifold? Very important, because on those manifolds things move. We understood, analyzed a manifold with its positive curvature, how it is locally homeomorphic to a Euclidean space. isomorphic to Euclidean space. We saw Riemannian manifold, which helps us to measure the distance. We saw what is a differentiable manifold, and we saw what is a Riemannian metric, a measurement in order to calculate the distance between points on a curved spacetime. So that's all. I just wanted to make this video sure that you understand each and every aspect of relativity, general relativity in a very easy way. So I will wait for your comments. Do let me know if you're unable to understand, and if you have any comments, you can mail me. You can have any conceptual understanding. There are a lot of people who are sending me WhatsApp message. You can do that. It is there in my about in the channel. You can email me. You can talk to me, whatever the way you want, and you can write to me. So do subscribe, like, and I take a lot of energy and time to make up this video so that it reaches you. So that's it. Thank you and have a nice weekend, and we will see you soon with some other more videos on general theory of relativity. Till then, goodbye and have a nice day ahead. Bye.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.